to do a lesson on improper integrals. So pretty much the same kind of thing that you normally do with integrals. All the process is the same. There's a little notation change. So an improper integral is one where the bounds, one of the bounds, it could be the top bound or the bottom bound. And what I mean by bounds are, if you remember, you have an integral from a to b of some function f of x dx. A and b are the bounds on that. So if one of the bounds is infinity, technically you're going to use the fundamental theorem of calculus where you subtract the bounds, and where normally we would take the integral from a to b of f of x dx, and we would evaluate b minus a, and we do all that. But we are going to use a limit notation because technically you can't throw infinity into an equation and be correct, because infinity is just a theory. It is not a finite value, so you can't just evaluate it the way you normally would. You have to use limit notations. So, for example, got this example right here. Got the limit from 1 to infinity, the natural log of x divided by x squared. Now, I purposely picked this one because it's the integral of this one is not necessarily the easiest thing to cover with you. It's not necessarily the fastest one to do, because you're going to have to use integration by parts. So if you remember that, so we're going to do a little side work. We're actually going to do the integral, calculate what the integral is, and we're going to really talk about working with the integral of the natural log of x over x squared dx. And we're going to integrate it and get that, and then we'll deal with what do you do then with the bounds. Okay, so if you remember our integration by parts, you have it on your formula sheet. If you need to get your formula sheet out and look at it, you by all means should. Remembering what we did with that is we picked a value to be u and another value to be dv. Whatever we pick to be u, we have to integrate or differentiate, and whatever we pick to be dv, we're going to have to integrate. So probably the best thing to pick to be u would be the natural log of x, because we definitely can differentiate that. We cannot integrate the natural log of x, so that's what we're going to pick to be u. And to pick dv, what we're going to pick is we're going to pick x to the negative 2 dx, because it's on the denominator, so I can move it to the numerator, and then I can apply my integration rules. So then du, derivative of the natural log of x, is 1 over x dx. And if I integrate dv, v would be negative 1 over x, or sorry, we'll write it as negative x to the negative 1 over negative 1. So if you use integration rules, you add 1 to the power, divide by that same amount. So with that, remember, using integration by parts, if I back up and I do a little side note on this, remember the integral of u dv is equal to u times v minus the integral of v du. So this is on your notes. This is on the formula sheet. That's the way we're going to rewrite that integral that's written in black. We're going to rewrite it using our values for u and dv. So we're going to write u v minus the integral of v du. Now we can keep on going. We've dealt with this. We can actually take care of the second the piece of this, which is the integral of that. What is now, this is negative natural log of x over x minus the integral of 1 over x squared, 1 over x squared dx. So if we think about this, this is negative natural log of x over x minus, if we do the same thing with this, remember that 1 over x squared is the same thing as x to the negative 2. So we would have that same value of x to the negative 1 over negative 1. And in the end, we have the negative natural log of x over x plus 1 over x. I think I missed a negative in there. Yeah, I missed a negative in there. Sorry. So let me back up, put that negative in there. There's a negative right here that I missed that negative. So go back into here, and there's a negative right there, which is going to make this negative, which is going to make this negative, which is going to make this part right here positive, which means we are going to have it like that. All right, so it'd be like that. So in the end, this is our integral. This is the integral we started out with. So way back in that purple one, this is our integral. So here's the deal though. If you were going to rewrite this, this is the notation that you'd want to kind of use. You'd want to say, okay, the integral from 1 to infinity, the natural log of x divided by x squared dx is equal to the limit as x goes, or sorry, b, we're going to choose a value b, it's on the top, so we'll use that letter to denote b, goes to infinity, the integral from 1 to b, the natural log of x divided by x squared dx. Those are the same thing. Now, the beauty of that is we can take our integral, which is right there written in black, that's what that integral is, and so we can write the limit as b goes towards infinity of negative natural log of x divided by x minus 1 over x evaluated from 1 to b. And here's where we plug in our bounds. Here's where we do the fundamental theorem. We plug in the top bound minus the bottom bound. So we have the limit as b goes towards infinity of negative natural log of b divided by b minus 1 over b minus negative natural log of 1 over 1 minus 1 over 1. So we have something like that. Oops, I forgot a parenthesis right there. So we have that. Now we start to talk about what this limit is. If you think about this limit as b goes towards infinity, this part right here is going to go towards 0. This part right here is going to go towards 0. This part right here is 0 because the natural log of 1 is 0. And this part right here is 1 So what we have is we have negative 0 minus 0 plus 0 plus 1. So our answer is just 1. Now you might have thought, why do we even use that? We could put infinity in there and kind of figure out what it is. Well, because technically if you put infinity in there, you've written something that's indeterminate. You cannot put infinity in for b. You have to use the limit notation and then evaluate limits. So pretty lengthy example. I'll back it all the way up so you can see the whole thing looks like something along the lines of that. Boy, I can't even get it all in one. So I can't even get it all in one. But the original, I'll kind of scroll through. You can stop it. The original problem looked like this. Remembering what integration by parts was, there's the original problem. Here's what it looks like when you do integration by parts. Here's what it looks like when you substitute it in using a limit. And then this is when you evaluate the limit. Hopefully that helps. There's a PDF that in the folder for today. The PDF has a couple more examples, and then it also has some practice problems, and the answers to the practice problems are right underneath it. So if you have any questions, I will see you at office hours tomorrow.